All right, so that's quantum mechanics and quantum chemistry basically going on there. This is solving the fundamental problem I mentioned right at the start, which is that the powerful models are not controllable. The deep neural nets have all these neurons like our brain, and you don't know which neuron to change to make it stop doing the bad thing, any more than you can go into the human brain and zap a neuron and now you won't do bad things anymore. It's too complicated for that. So one way to fix that is with Kolmogorov-Arnold networks. So we'll start by doing a curve fit to understand what they are. So first we're going to fit some data. So here you have some data, and you can fit it with just a polynomial of degree 2, and you'll get the best fit. This has been known for centuries. All right. Now, if the degree is too low, like a straight line, you get this, which is terrible. If the degree is too high, then you get these crazy wavy things that go too far. And if you have fewer points, then that messes it up. And here you get, all right, so here's a more complicated one you can fit with various polynomials. So that's the first thing, just understand how you can fit different complex curves with polynomials. Now, let's do B-splines. Instead of fitting things with polynomials, B-splines look like this. You're going to fit this curvy thing with B-splines. K equals 0 are just square waves, just a flat value. So this is like the decision tree. Order 1 will draw straight lines between adjacent points. Order 2 will fit parabolas between points, doing better and better fits. And you can have higher orders like order 3, where it gets pretty good. Notice, by the way, at the end it has a deviation because it's trying to fit points that are off the end. And since those points are missing, it distorts the curve. So you can fit that with these B-spline basis functions. What you're doing is you're combining these basis functions. K equals 0 are just step functions. It's 1 for a certain region and 0 elsewhere. The next one is 1 up here and 0 elsewhere. So that's why you just get that straight line fit, like a digital analog converter. K equal 1 has straight lines going up and down for each one. So if this is what creates straight lines between the adjacent points. These are Gaussian-looking things that make the parabola one, and here's a similar one that makes a cubic-looking one. These are called B-splines. The important thing to understand is you can make a curve out of a superposition of these, just like you would with a polynomial, but each one of them only has a local effect. So the result is, now, when you're done making a model here, and you have a bunch of parameters, you know what the parameters are doing. It's interpretable. The parameters here only affect the data near here. If you don't like this, you know which parameters to adjust to fix it. These parameters over here don't matter. The parameters have a local effect. So you actually understand what you're doing. And I say it can be as powerful as deep neural nets for a lot of problems and much more interpretable. So this is one possible area of improvement as we make models solving that problem. By the way, I should mention, I mentioned catastrophic forgetting. There's another issue. If you do train your model, like they did on this huge heap of data from the internet, and then say the New York Times wins their lawsuit and says, okay, you have to take the New York Times data out of there. There is no way to remove data from the model. There is no known way. People have tried. That's very complicated. The only way to actually be sure you've removed the data is to throw away the model and retrain a new model on the data set, which is real expensive. And that's related to this not being in control. If something's wrong with your model, you don't know how to change those weights to make it stop doing that bad thing. And there's no way to control the forgetting. There's no way to prevent the catastrophic forgetting, and there's no way to induce desirable forgetting. Not unless you could actually understand what neurons are doing. Here, though, you could give your model some degree of a lobotomy and have some limited damage. You'd have some idea which neurons are participating in which part of the calculation. That's the idea. We'll see how far it goes. Anyway, I think that's probably enough.